It's Friday, 4 p.m. Doing a little Diffie-Q. The stream link is coming in a second. There it is. So we are streaming. Let's check out the lecture announcements. I got my rig all figured out. Nothing disastrous, too disastrous happened. I didn't have to rebuild anything, so that's good. Okay, to-do list. What do we got on deck? Well, we're talking about phase diagrams. Worksheet number 12, that's coming in today. A-level work is on Wednesday of next week, FYI on that. The final exam is scheduled for May 10th that's a Monday at 1 p.m. And then we've got one web assign and one worksheet left. And then another announcement that I'll give is that for another project that I'm doing, I went through fall 2020 archival footage, and while I was in there, I grabbed some stuff that might be useful or just generally interesting for our needs. And so those things are posted to YouTube. They're unlisted. And so what I'll do is this weekend, when I get a chance, I'll make an announcement, because I found some things too, like some review for final exam of fall 2020. And so I have those things, and I'll post it to the announcements for our sections. And then you can take a look at those if you want, and they have timestamps so you can navigate them easily. But I mean, it's already done. I figured you might use it, so I'll make it available for everybody. And what was I going to say? Oh, yeah. Our final exam that's on May 10th, we are almost done with the drafting phase of that. And last fall, we released a practice final exam ahead of the final exam, and we intend to do the same this semester. The practice final exam and the final exam will be on WebAssign. And then that way you can get an idea of break up over the comprehensive material to give you guidance in terms of how you prepare and stuff like that. And that'll be released on Monday. It's not for a grade. You don't need to do it, but definitely if you're preparing for the final exam and that's something that you want access to as a preparation tool, then that'll be out there. So I'm going to cut out on the lecture information, bring in our to-do list. Specifically, we're looking at phase diagrams. We're going to start up the trace determinant plane today. How are we going to get this done? Oh, these 37 should be 38. Skrrr. 45 participants. Oh, we're up to 50 now. And then we're going to review real roots, talk about degenerate roots, talk about complex and imaginary roots, and talk about the trace determinant plane. We're going to graph stuff. You are, I think, only responsible for 2 graphs on the next worksheet coming, right? And so I'm going to try not to get too heavy into the graphing and more from picture-based recognition. That's really where we need to be, but I like to graph stuff, and so I spend a little too much time geeking out about that. And then Lucas in chat says something about degeneracy. And I think last semester, one of the key sound bites I heard coming out of a class is that we're going to talk about an unstable degenerate node. Or, I mean, it gets talked about. We're talking about a stable one. And so students said that they were going to use that as an insult going forward. I thought that was pretty minds-like. So I'm going to transition over to the pad. Going over to the pad. This is our first page. I didn't get a chance to get this up to the drive today. Before class, I was too busy messing around with putting these animated GIFs in here. And so let me bring back my talking head. There I am. And so what we really want to do is we want to understand, 1, why these pictures exist, and 2, how the pictures are related back to the eigenvalues. Because what we really have here is a classification system for our phase diagrams, and these diagrams are coming from x prime is equal to matrix A times x, which can be thought of as coming from AY double prime plus BY prime plus CY. So these could all be thought of as some sort of relationship with those problems, and some of these are mass spring-like in nature, right? But really what we like on the mathematical side is it paints a broad brushstroke and gives us a classification scheme on a variety of different mathematical problems. We love that stuff on our side. We're like, oh, all these problems, they're just like this and like this and like this, right? And we make groups. We organize. That's part of what we do. Okay. So the first thing is that we need to recognize that these are all coming from x prime is equal to matrix A times x. Okay. Next, what I want to do is I want to highlight this case right here, the third bullet point on point number 1, and that is what happens if one of my eigenvalues is negative and one's positive, or one of my eigenvalues is positive and one's negative. The main point here is that you get two eigenvalues, they are real, and they have different signs. Okay? Well, in that case, because of one eigenvalue being positive, that one eigenvalue being positive causes an instability in the system. What do I mean by instability? I mean that the styrofoam peanuts that are being defined to move around the plane through the vectors that are specified by the differential equation, the majority, or basically all of the styrofoam peanuts, are being thrown out to the boundary of the plane. They're being sent out to a spatial infinity, if you want to think about it that way. Okay? Now, how do I get an idea of this plane? Well, the eigenvalues are tied to eigenvectors, and those eigenvectors, when scaled, form lines in space. So what we want to see in this computer visualization that's embedded here is that there's a line in space that goes from the lower left to the upper right, and on that line in space, we see that the styrofoam peanuts are going out towards spatial infinity, flowing along the direction defined by that line. There's another line going from the upper left to the lower right, and what we see are styrofoam peanuts that are flowing into the origin along that line. So we have a positive eigenvalue giving us growth, a negative eigenvalue giving us decay. That sets up the lines, and then trajectories will follow one line in, then eventually get bounced out in favor of another line. One line in, bounced out, follow one line in, bounced out, one line in, bounced out. And that very crude green drawing that's written over the top of the lovely computer visualization is indicative of a saddle shape, right? And so we call this an unstable saddle. Maybe you want to use the word node. And what are we talking about? We're talking about this origin. The origin is the equilibrium point. We're looking at trajectories relative to that dot in the center, and all we care about right now is the origin. On Monday, we'll extend this to other points. Okay? What else can I say? I can also tell you that if both eigenvalues are negative, then now on these lines in space, the arrows would point inward, right? Both lines exhibit decay. When they both exhibit decay, what do I want to do here? I want to highlight that both eigenvalues are negative, and when both eigenvalues are negative, the system is stable. So the word stable is used to indicate that what you have on deck are decaying exponentials. Those decaying exponentials are going to cause all your styrofoam peanuts to go to one place, and that place is the origin. And so we got the origin dead in the center of this graph. All the styrofoam peanuts are flowing in there. But since my eigenvalues are real, they also have eigenvectors. And since the eigenvectors form lines when scaled, I get two lines in space. There's one line that we can see. There's another that's coming from the upper left to the lower right. And on these lines, we see decay. So the arrows point into the origin. And since they point into the origin, I have that stability. And now I want to think about what the styrofoam peanuts that are doing that are not on these brown lines. And there are two things that could happen. I could do one thing, which is to come in the way the graph indicates. Things could come in this way, following this north west direction, and then bending back around to follow the northeast direction into the origin, right? But they could also come in this way. We know that's not happening because the computer visualization says that it's not. But then what do I have to do to figure out the difference between those two? I have to look at large time values and figure out which eigendirection, which eigenline is driving the styrofoam peanuts show. And in this case, we see following the northwest direction until the end where I follow in on northeast. And so I get trajectories that look something like this. Oh gosh, those look horrible. Especially against that computer. But anyhow, so I get styrofoam peanuts going into the origin, and they use these eigenlines as runways as they do so. I don't know why I've colored all this brown. I started coloring things off as purple over here, so let me make that consistent. Here's purple. And I have my real stable sink. Now for this last one, I'll do purple. And with purple here, I have that both eigenvalues are positive. Those eigenvalues being positive are causing an instability. So I call this unstable. I think about sources as unstable. I use those terms analogously. And then this third graph down in the lower left has a line running from the upper left to the lower right. On that line there is growth. And then I have a line going from the lower left to the upper right. On that line there is growth. And again, I could have things coming out of the origin following northwest before bending around northeast. Or I could have things coming out of the origin, styrofoam peanuts flowing northeast and then bending around northwest. How would I figure out the difference? I would look at large time values, both positive and negative, but it doesn't matter. The computer tells me that it comes out of the origin northwest, bends back around northeast, comes out southeast, bends back around northeast, comes out northwest, bends back around southwest, and then we get this shape right here, and that is indicative of a real unstable source. So, why do we do this? Well, notice that everything is mapped back to the eigenvalues. All that can really change about these pictures, if I keep the eigenvalues grouped the way that I already have, is that all that can change with these pictures is I can take these eigenlines and then I can change their orientation so that they're still linearly independent, but they're not orthogonal like these nice graphs are. And if I do that, I can make acute and obtuse angles, but these curves that I'm drawing, they'll still stay smushed in these little wedges or in these big wedges out here. But otherwise, every saddle looks about the same. Every real sink looks about the same. Every real source looks about the same. And I can tell that from the eigenvalues. If I do not need to get down deep and figure out how aligned or what's the angle formed by these two eigenlines, then I don't have to. I just need to know my eigenvalues. So now that we know that it's tied back to the eigenvalues, I know that I have complex and repeated eigenvalues, and we would like mugshots for those things too. But that said, are there questions? So I'm going to fade, I'm going to freeze and let you take any last photo or any notes that you want. And then I'm going to switch us over to a repeated root eigenvalue problem that we had looked at prior. And it's the original slide from, I think, lecture 36 or 35, somewhere in there. And then we're just going to clean it up and talk about the graph. Moving over in 3, 2, 1. You might remember this fun show where we have a matrix, we solve for its eigenvalues and eigenvectors, we find out that an eigenvalue is repeated, which gave rise to only one eigenvector. Here is some of the work that we did to show this. I'm going to erase this work, and I'm going to just grab our final solution that we have down here, because that's the thing that we need to inspect. So let me erase this stuff. Delete, erase, grab, and then I think some things have gotten erased over time, so let me put them in. There's a 1, and then there was probably another parenthesis hanging out here. Okay. Then I'm going to fade back in. There we go. This is our repeated root case, and here's our solution, and let's just take some notes. First note. As t goes to infinity, we get that the x function goes to 0, 0. Why does that happen? Well, as t goes to infinity, check out the eigenvalues that are in all these exponents. All these eigenvalues are negative 2. Right? It's my only eigenvalue, but that eigenvalue appears up in the exponent, and that's what's going to drive the show, the dynamics. And as t goes off to infinity, all of these exponential functions decay away. The one that's questionable is, okay, if there are terms, I'm going to point the cursor at the first term. I'm going to get the laser pointer out for the second term. And then the last term I'm not going to do anything with. I will call them term 1, term 2, and then the last term that has no pointing towards it, there's term 3. So term 2, that's the questionable one. As t goes off to infinity, this t out front is getting large, but this exponential is getting small. And ultimately, when t goes to infinity, the exponential wins, and if we had to prove that, that would be a statement of L'Hopital's rule. So, as t goes to infinity, everything goes to 0, and so this is talking about a stable sink. The decay of every single term is telling me about stability. Okay? So I know that at the end of the day, in my phase diagram, which I'll start up over here, this 0, 0 is at the origin, and everything must end up at the origin as time gets large and goes to infinity. The real question is, how does it go there? In the previous examples, we've seen that runways, these eigenlines, are taking things either to the origin or away from the origin, but guiding the direction. So, now I start making the arguments, if t is much, much greater than 1, the x vector is approximately... Okay, so check this out. Look at the general solution. There are 3 terms. As t gets really, really big, all 3 of these terms decay away. But there is one term that's just trying to hang on at the very end. But everything else is decayed away to 0, and it's like just trying not to go there. It's the last to the finish line. Which term is that? Term number 1, term number 2, or term number 3? Term number 2, right? So what that means is that in the large time limit, the solution is basically C2, 1, negative 2, t e to the negative 2t. That t is just holding on for dear life as it's being sucked into this sink. And then plus a little bit, right? This is an English language statement added to a math equation. That's not very proper, but it's saying that there are a couple other terms hanging out, but they're basically 0. And term number 2 is basically not quite as much 0 as the rest. Can we call it an eigenbit? Yes. I think that the reason why the term eigen still persists within the mathematics is because, yeah, you can put it as the prefix to tons of stuff, and it's great fun. Right? So, yeah, you got term number 2 plus an eigenbit. Now, if t is much, much less than negative 1, I got x of t is approximately, okay, now I'm really far back in time, right? I'm in negative times, but if I'm in negative times, I have e to the negative 2t times a really large negative number. So instead of decaying away, all 3 of these terms are blowing up. Now the question is, as they're blowing up, which one's blowing up strongest? Well, because of this...
1 and 3?
1 and 3 are blowing up, right? Because these guys have positive exponents. They're blowing up. This has a positive exponent. But if t is really large and negative, check this out. There's an extra t right out front. It's causing that second term to have a little bit more stank on it, right? It's blowing up, and it's like, no, I'm racing ahead of you guys because of the t multiplier. And so I have C2, 1, negative 2, TE to the negative 2t plus an eigenbit. Okay. And Lucas's comment is, or point is well taken. Lucas's point is well taken, and that is, in all of the previous examples, we had some sort of trade between one term and the other term, both forward in time and backward in time. In this case, for repeated roots, there's only one term with one direction that drives the dynamics forward and backward in time. Okay, that's the strangeness here. What term is that? Well, it's the t multiplied term. And so, if I take a look at it, what's driving the directional show here is this eigenvector 1, 2. So let's graph it. I go 1 in the x direction, negative 2 in the y direction, and I draw a line in space going through the origin, touching that point. And now, because the exponentials are both negative, and I've noticed that brown dot, things are trying to get to the origin, there's decay on this line. What would the difference be from t much bigger than 1 and t much less than 1? You mean yeah, I think what's being asked in chat now is, I got it, that this eigenline dominates both for large time positive and large time negative. What happens in between? Maybe. If I'm wrong on that interpretation, definitely chat more and let me know. But there's a real question of what's happening all the way in between negative time and positive time, right? What happens in this area? Well, it depends. There are two things that I think could happen. If I'm really far back in time, I could be following the green line. I could parallel it, right? Because there's the direction defined by the green line. And I could go, but then eventually, where do I have to go? I have to go to the brown dot. And so eventually I'm going to say, oh, I've got to bend back around. And when I bend back around, this green line is the runway drawing me in. So I could do that. I could get this shape going on. But I could also have, okay, I'm paralleling the green line still, which is what you told me to do. And then I go forward in time. Now I'm at small time values, maybe positive. And then eventually I'm like, oh, I got to find this eigenline again. And I got to follow it back in. I don't know why I'm looking at the screen while I'm drawing this. That's a horrible idea. I should look at my hand, actually. There we go. That's better. And I come in, right? And I could have one of those two paths, right? But I don't know which. So the question is, how do we flow to 0, 0? Answer, check a point. What do I mean by that? Okay, so I'm going to put in purple right here this point in space, and that point in space is at 1, 1. So what I'm going to do is I'm going to take A, multiply it by 1, 0. I don't mean 1, 1, I meant 1, 0. And so that's the A matrix, which is 0, 1, negative 4, negative 4, times 1, 0. And when I do this matrix multiplication, I do a 0 times a 1 plus a 1 times a 0, which is a 0. And then I do a negative 4 times a 1 plus a negative 4 times a 0 for a negative 4. And so what is this? This vector right here, which I'll highlight in orange, the 0, negative 4 vector, is saying if you're at the purple point, if you're at the tip of I hat, when I multiply that point by A, that's telling me, hey, what is the vector field doing at that point? And the vector is 0, negative 4. So it's saying the vector field is pointing downward at that point. And if that's the case, that must mean solutions are coming out, following the green line, and as the green line weakens, I hit this point right here. Oh, gross. I hit this point right here, And then this point is saying, yo, the vector field's pointed straight down right here. So I'm pointed straight down. So now I'm really starting to see that green line. And the green line says, yo, turn it back around and go to the origin. Follow me. And so I get something like this. So I get solution curves that come out of quadrant 1 into quadrant 4 and wrap back around. And then I do the same thing. I could test a point down here, but I'll get a swirl that comes out of quadrant 3 into quadrant 2 before it gets wrapped back around. The point 0, 0 is called a degenerate or a stable degenerate sink. So in the event that we have one eigenline, that eigenline runs the show both forward and backward in time. And so solutions have to come in parallel to that eigenline and then be bent back around and become parallel to that eigenline again before ultimately they go to the origin. So I'm going to fade out and freeze. And what I'm going to do is I have a computer visualization that I'm going to go grab of exactly this. And so let me get that and then we'll paste it in. Okay, I've got it ready to go. I'm going to come back in 3, 2, 1. So there's a computer visualization of our styrofoam peanuts, and they do exactly that. They come flying out of spatial infinity and then get wrapped back around as they follow this one and only one line into the origin. The fact that I have one eigenvalue, that is what the degenerate term means, and then this is stable is saying that the eigenvalue is negative, causing all styrofoam peanuts to go into the origin. Okay. Questions about that? All right. So, previous cases, you have two eigenvalues that are different. You can get saddles, sinks, and sources. There are two lines in space that guide the styrofoam peanuts. You can get a degenerate case where you only have one eigenvalue. If it's positive, you get a source. If it's negative, you get a sink. But the real point is that there's only one line in space guiding everything. Now, the last case is the case for complex roots. And when you have complex roots, you have no lines in space anymore. So I'm going to move us over to that. I think that this A matrix needs to have like a negative right here. I think that's a mistake. So what we have is, and it was probably from a cut and paste, what we have here is a set of work from the first time we encountered imaginary eigenvalues. And wrapped them up in differential equations. And so what I want to do is I want to keep the eigenvalues. So I'm going to keep this stuff right here. And I'm going to excise all this stuff in favor of just keeping the final solution, because with that final solution, I'd like to talk about the associated graph. I'm going to take all this stuff, delete, and then I'm going to grab this solution right here and bring it up. Okay. So, notes. There are no straight line solutions. So all of our graphs prior were all about building off of those straight line solutions, and now we don't have them. And since we don't have them, we're going to have to be a little careful about how we study this, and maybe we're not going to be able to get the same level of detail that we had before. So I'm going to get my phase plane set up. My phase plane will have the origin as the equilibrium solution. And so, since there are no straight line solutions, the trajectories will circulate about 0, 0. Okay. How can I see that? One way to see that is, suppose we consider the point x of 0 is equal to 1, 0. So where do we want to consider? We're doing the same thing that we did before. We consider one point in the plane, and that point is at 1, 0, so it's at the tip of I hat. But if x of 0 is 1, 0, then that means I get b1 times cosine of 0, which is 1, sine of 0, which is 0, plus b2 times the sine of 0, which is 0, times the cosine of 0 with a negative, which is negative 1. And so what do I find out here? I find out that b1 is equal to 1 and b2 is equal to 0. So at this point, my solution is x of t is equal to cosine of t in the first row and then sine of t in the second. And so, let me write this out the way you'd write it out in Calc 1. Or not Calc 1, Calc 2. Maybe Calc 3. Bracket cosine of t, sine of t, bracket. If x is if little x, scalar x, is cosine of t and scalar y is sine of t, what's the shape that's made?
Circle.
Yeah, these are circles. Does it go counterclockwise or clockwise? So I start at this point right here. I make a circle. There's my circle. Do I go counterclockwise or clockwise, you think?
Counterclockwise.
Counterclockwise, yeah. So the arrows point that way. Okay. So what is this diagram? It's a whole diagram of circles. All these circles trace paths, closed paths around the origin. And 0, 0 is a semi-stable, which we'll talk about in a second, center. Okay. So center is the language here. And semi-stability is that as I come around on my closed loop, if the slightest nudge were to happen to me going into the origin or away from the origin, I wouldn't arrive back at the point that I started. So it's a very fragile sort of stability. I'm going to fade out and I'm going to freeze because I'm going to go grab the diagram, the computer visualization of this, bring it up. Then I'm going to come back in 3, 2, 1. There we go. Those are the styrofoam peanuts flowing in a circle around the origin. And so when we get imaginary roots, we lose any straight lines that we had prior, so we don't have that scaffolding to graph off of. And if we have purely imaginary roots, right? We get this structure right here, which are closed curves. Right now they're circles because I wanted them to be circles, because you might have remembered parameterizing the unit circle, but in general they could be ellipse. Circles are just a very special form of an ellipse, right? Where the major axis and the minor axis are the same. So you can define a radius. Okay. So then the last question is, okay, this was purely imaginary. My eigenvalues were plus or minus I, right? The i's are telling me about the sinusoids, and the sinusoids are what are breaking the straight lines, and we're getting circulation as a consequence. The last question we want to address then is, what happens if we don't just have imaginary, we have proper complex, which is imaginary with a real part. So let that hang for a second. Then I'm going to move it on to this problem, which you might remember from a previous lecture. How could you forget these square roots of 11? I have fond memories of those too. So what I'm going to do here is I'm going to scrap out the work to get the eigenvector, the work to get the eigenvalue. I will retain the eigenvalue. I'll retain the matrix. And then we'll take a look. So we have all this good stuff from before. And then you might remember the very fun time we had when we moved to try to find the general solution, which we did. So those are the relevant results. But here's the big idea. Now we have this -1 appearing in my eigenvalue. I got this square root of 11i, but that square root of 11i, that's going to cause sinusoids. And in the example we just saw, the sinusoids are going to cause circulation, right? Now what I want to think about is what happens when I get this real component in, and where does that real component go? That real component goes into this exponential. So if these sines and cosines are causing the circulations, now, because of that -1 is a real part, I have e to the -t out in front of everything. So what that means is when I circulate, I'm going to come back around. But because of that e to the -t, every time I come back around, I'm smaller in x and y than I was before. So ultimately, all this stuff, as t goes to infinity, it's all going to circulate or spiral, and it's going to spiral into the origin. So the note that I would take here is that as t goes to infinity, all of my styrofoam peanuts go to the origin. And because we have the square root of 11i, this implies circulation. And so what this tells me is that if I get a complex eigenvalue with a negative real part, things are going to go to the origin. They're going to circulate as it does that. And what this is called is a stable spiral, or what some people will call complex sink. This is different than the real sink. I get that all the styrofoam peanuts end up at the origin, but in this case, they spiral as they do so. And we have like a proper thought process of a sink, like a bathtub where the water spirals down in it. And And yeah, let's think about graphing. So here's my plane. I'm going to move my head over here because what I'm going to need to do is the same thing that I did before, right? As I spiral down into the sink drain, right? I could do so Australian style or I could do so American style, right? There could be a polarity difference. And so I'm going to pick a point. I picked the point 1, 0, and then over here in the upper right, where my head normally goes, I'm going to take a look at A times the 1, 0 vector, but my A matrix is -3, -5, 3, and 1 times my 1, 0 vector. When I do this matrix multiplication, okay, what's my 1, 0 vector? That's the point in space where I drop the styrofoam peanut into the toilet relative to some toilet coordinate system. And so I get a -3 times a 1 plus a -5 times a 0, and I get a -3. Then I have a 3 times a 1 plus a 1 times a 0, so I get a 3. And so at that purple styrofoam peanut, what is the instantaneous direction saying? At that purple styrofoam peanut, this is saying, hey, you need to go left in the X direction and then up in the Y direction, right? So I need to go up and to the left. And so if I were to drop my styrofoam peanut into that purple location, what's going to happen is I go up and to the left. And then as I flow, I circulate. I come back and try to hit that purple spot again, but I don't because my amplitude's decaying. And I keep oscillating and circulating until ultimately I get to the origin. And so I put arrows on this indicating flow. And that is my stable spiral sink. What would happen if the real part wasn't -1, it was a +1? Where would everything go then? Yeah, it'd be a disaster, right? Yeah, it'd go outwards through infinity. This is a good toilet. If this -1 were a +1, it would be a bad toilet. And you'd call it an unstable spiral source. So I'm going to fade and freeze, and I'm going to go get the computer-generated diagram.
It would make the toilet a lot more enjoyable, a lot more memorable.
Memorable, true. Enjoyable, I might disagree.
It's a bidet.
Oh, man. I don't know how much more of this I can support. This seems sketchy already. Okay, I'm going to come back in. I'm going to... Whoa, that's the wrong knob. There we go. And unfreeze in 3, 2, and 1. There we go, and that's the computer-generated diagram. So we're not going to be able to be as precise on these because we don't have the straight line solutions guiding us, but we can at least get an idea of whether the good toilet, much to the chagrin of Lucas, is going clockwise or counterclockwise, and we can tell if the styrofoam peanuts are going into the origin, behaving nicely, or coming back out. Design project fall 2021. Awesome. For my design project, I have made an unstable spiral source in real life. I know, right? Every time I see it, I think about like some picture from astronomy, like some galaxy. All right. Well, those are the diagrams. Stable spiral sink. If the eigenvalue were to have a real positive part, then it'd go out from the origin instead of in. If the eigenvalue has 0 real part and only imaginary part, we get circulation, pure circulation. If the eigenvalue is repeated, there's only one eigenline to follow. If it's positive, it's out of the origin. If it's negative, it's into the origin. And then if you have 2 eigenvalues that are different, you could get sinks, sources, or saddles. That's your family of mugshots. All And then the last thing I want to talk about is organization. What we've done, we've taken this matrix ODE problem that's rooted in eigenvalues and eigenvectors, and we've now just classified it into 8 typical mugshots. Okay? Those mugshots are tied back to the eigenvalues. But you might remember that when we calculated the eigenvalues, I had brought up traces and determinants. So, if the eigenvalues dictate the type of phase diagram, then let's remember that the eigenvalues are determined by trace and determinant. Thus, the phase diagram is determined by trace and determinant. Let's remind ourselves. The trace of the matrix A, I will write down as capital T, or your book will use the Greek letter tau. I'll clean this tau up a little bit. Vertical line, and then a top with a little curl on it. There's my tau. And that is A plus D, the sum of the main diagonal elements. Yeah, supermassive black holes are stable spiral sinks. Crazy, didn't ever think about that. All right, and then the determinant, which is D, in your book is represented by a delta, and it's going to be the typical way to calculate determinant. So what that means is that if I look at the determinant of A minus lambda I, that's going to be lambda squared minus the trace of lambda plus the determinant. I'm going to set that equal to 0. But that's just a quadratic equation. I have a formula for that quadratic equation, and that formula is that lambda, you should be equal to negative, well, there's a negative trace hanging out there, plus or minus the square root of negative trace squared minus 4 times determinant all over 2. And so I get trace plus or minus the square root of trace squared minus 4d all over 2. So where am I going with this? The idea is that lambdas tell us the picture. And what I want to know is, if you give me a system without having to calculate all the solution, can I get an idea of what picture the system makes? Well, I can, because lambda is a function of trace and determinant. So what I'm going to do is I'm going to set up a plane. This plane is not the phase plane. This plane is a plane to just organize the information. And on the horizontal axis, I'm going to put trace. And on the vertical axis, I'm going to put determinant. And now I'm hoping, well, first I notice for every single point, like this point right here where the tip of the cursor is, at the tip of the cursor, there's some trace value and some determinant value. Let's say 2 and 3. But if you know trace is 2 and determinant's 3, you know all that stuff. But if you know all of this, then you know the eigenvalue. But if you know the eigenvalue, then you know the picture. Okay? So my hope is that the eigenvalues with respect to trace and determinant are very well organized, and we'll talk on Monday that organizational structure, but it turns out it is absolutely organized. In that plane, if your trace is positive and your determinant's positive, you are some sort of source. If your trace is negative and your determinant's negative, you're some sort of sink. And if your determinant's negative, you're some sort of saddle. And so that means that I am capable of understanding only the trace and the determinant, and then boom, I instantly have a picture associated with the system. That's what we're going to look at next time. But that ends it for today. Have a good day. Enjoy your weekend. Best of luck.
Recording stopped.